Hi students, hope you are doing well. Today we start optimization tutorial 4. I'm going to discuss rate of convergence, an important concept in algorithms and optimization. I'm Dr. Ganguly. So what we are going to do is that we are going to use the steepest descent method or the gradient descent method to figure out its rate of convergence and also something known as the rate constant. So essentially we are going to use the Python code to solve this problem. We have developed this Python code in previous classes. Today I'm going to slightly change the Python code so that we can calculate the rate constant and so on. Now just to recapitulate, the gradient descent method says that dk is minus ck being the gradient vector, and xk plus 1 is xk plus alpha k dk, where alpha k is the one-dimensional step size and dk is the search direction. So of course you know that dk, the search direction, is different for different methods. The steepest descent method has one of the simplest search direction that is given by the negative of the gradient vector. So if you have calculated the gradient vector at any point, you can essentially use the steepest descent method. Now if you are interested in the lecture and theory, look at lecture 14 for rate of convergence and lecture 13 for the steepest descent method. Now let us look at the concept of rate of convergence. So essentially what happens is that whenever we have an algorithm, there is a sequence, and the sequence is something like x0, x1, x2 all the way to the point where the algorithm hopefully converges. So you can see here that x superscript k, this is the kth point, and x star is the actual solution. In this case, the optimization problem, it's the optimal point. So at each step k, we are going to have a difference between whatever the algorithm is giving, which is x superscript k, and the actual value of the solution, which is x star. So this difference is actually a residual, an error, and we call it e subscript k. So now hopefully what's going to happen, that if the algorithm is going to converge, then ek is going to become equal to 0 as k becomes larger and larger. So of course theoretically this limit takes place at infinity, but for practical purposes, for practical algorithms, you want this to be some low finite number. Now what we can do is we can define this statement here. This is a very important statement, and this statement says that in the limit as k tends to infinity, the norm of ek plus 1 divided by the norm of ek to the power r is equal to c. Now in this definition, r is the rate of convergence and c is the rate constant. So if we were to actually run a particular code, run the algorithm and get these numbers, then we can find the value of r and c which satisfies this particular equation here, and based on that we can figure out the rate of convergence of the algorithm and the rate constant c. Of course c has to be less than infinite so that this makes sense from a practical perspective. So again, to recapitulate, r here is the rate of convergence and c here is the rate constant. These are two very important concepts in convergence of algorithms. Now the special case which we have for the gradient descent method is linear rate of convergence, and this happens because r equals 1. So of course what we can say is that if we forget about this infinite, we could define this rate constant and rate of convergence using this equation here. So hopefully as k becomes larger and larger, this is going to converge to some value, and this particular equation should hold at most values of k, and in fact it should hold at all values of k in some cases. So what happens when rate of convergence is 1, that you have this equation here, that is norm of ek plus 1 equals c, the rate constant, into norm of ek. So this should certainly hold for the steepest descent method, which is known to have linear rate of convergence. So what do we choose for ek plus 1? Now remember that x here is a vector, that is the vector of design variables, and therefore it's going to have different numbers. We could take the norm there, but actually we have a value which is very much useful in terms of tracking the algorithm, and that is the function value itself. So essentially we could use the fact that ek plus 1 could be defined as f x k plus 1 minus f x star. So essentially at the k plus 1th point we calculate the function value and subtract it with the function value at x star. Now x star is the actual converged value for the solution here. In many problems you may know it, and in some problems if you don't know it, hopefully the algorithm itself is going to converge to x star here. Now this is divided by ek, and ek can be expressed as fxk minus fx star. So what the function does is that it essentially brings down the dimensionality of the problem. So instead of using, for example, n variables in the design vector, we can use only one variable, which is the function value. Suddenly we are dealing with single objective function here, so this should suffice. Now let us turn to the question, which is we want to write a Python code for gradient descent to find the rate constant. And we are going to assume linear convergence rate, and we again use the function which we have used several times before in this course, which is fx equals x1 square plus 2x2 square plus e to the power minus x1 minus x2. And we are going to start from the point 5 minus 5. So let us build up the different Python functions, and then we are going to look at the main program. So the first function we build up is actually to calculate the mathematical function. So this is the Python rendering of x1 square plus 2x2 square plus e to the power minus x1 minus x2. So I calculate this exponential term using this term here. So I have to invoke numpy. So I bring np.exp here. Exp is the exponential function. Now for calculating grad f, I need to actually return this vector, and again grad f in this function can be obtained by simple differentiation. So the first term is obtained by differentiating with respect to x1. That gives me 2x1 minus e to the power minus x1 minus x2. And the second term is obtained by differentiating with respect to x2. So I get 4x2 minus e to the power minus x1 minus x2. And that is put here in Python. So again, you see that this particular function grad f is going to return the vector to me, and this vector is going to be the gradient of the function. Now finally, I have one more function here which is going to be required to do one-dimensional search. And what this function does is that it returns the value of the function at k plus 1, or rather xk plus 1. So remember, xk plus 1 is xk plus alpha k dk. So what this function is going to do, it's going to take in some input value of alpha, some value of d, the search direction, some value of x, the current point in the design space, and it's going to return to me f x plus alpha into d, which is essentially f at x k plus 1. Let us take a look at the gradient descent function. So essentially this is the function here. So we start off with the starting design, or the initial point x is x0, and then for I in range max I do this calculation. That is, I essentially declare d as negative of the gradient vector here, and the gradient vector is obtained by calling grad f. I then obtain alpha value by calling a one-dimensional search here, and then essentially I print out this alpha value, that is the one-dimensional search parameter. Then I print out x, the current design vector, and I also print out f of x. Now in contrast to previous programs I have written for gradient descent in this course, here actually we are tracking fx also, because we need that for the convergence rate. So essentially what I do here is that I am going to put this fx into a list known as f history, which I am passing through here. So what this is going to do is that each time you go through this particular loop, it's going to put the current value of fx into this list here. That's going to give me access to all the time history of the f values. So I will know f at x0, x1, x2 all the way to xk and xk plus 1. Now of course I have the breakout statement, which means that if the norm of the gradient is less than tolerance, which is a small number, then I essentially break out of the for loop, and finally whatever happens I return x and I here. So I return the design vector. Hopefully if this algorithm has converged, this is going to return to me the optimal value, and it's also going to return me the I at which this algorithm has converged. Of course, I also need the one-dimensional search here, so I have put it in this particular function. We have discussed this several times before, but let's go through it quickly. So we start with alpha is 0, we set some large value of I, and we choose delta, which is the change here in alpha each time you go through this algorithm as 0.05. That's the delta. And then I have this for loop here. Now I continue doing this for loop as long as I is greater than tolerance, which is a small number, and I have some large number of loops through which I go through here. Each time what I do is that I increment A and I get AL, I get AM, I get AU, the lower bound, the middle bound, the upper bound. I compare the function values at these points. Remember, I'm using the function f1d, and then I figure out the point at which the function has come down and just started to increase. So that's the point at which I bracket the minimum. Then I declare the minimum point to be the mean value of those lower and upper bounds, and I is going to be the difference between the alpha upper bound and alpha lower bound, and I set the new alpha as the alpha lower bound, and I decrease delta, so I divide here delta by 10. So each time you go through this particular system, you are going to bring down the interval more and more, and in the end this method is going to converge, and I'm finally going to return A star, which is essentially the optimal value of alpha for this problem for the given dx at the current iteration. Let's now look at the main program. Now one more thing I need here in this main program is I need to know what is the fx star, which is the optimal value of the function. So for that, if you remember from tutorial 3, the optimal value can be expressed in terms of the Lambert W function. So in that case, x2 was 1 by 3, Lambert W 3 by 4, and x1 was 2x2. So these are the actual exact solution for the problem. Now fortunately in Python, I have a particular resource or library called scipy, and if I bring scipy.special, which gives me some special functions, I can import Lambert W there, and then I can immediately write x2 as Lambert W 3 by 4 divided by 3, which is this here, and x1 is 2x2, and I can then calculate f star using f and sending into f this particular vector. So that's going to give me the particular value. Now I'm going to print this exact solution here, exact x1, exact x2, and exact f star. Now of course I'm going to do the steepest descent algorithm here. I'm going to start with the point 5, -5. Again, I start this list f history to track all the values of f. Tolerance is a small number, max is a large number, and I have this function steepest, which is going to return me x star and k. That is the optimal point, the number of iterations it took to get to the optimal point, and also it's going to return to me this list f history. Then what I'm going to do, I'm going to print these values x star and k, and I'm also going to take this f history and I'm going to calculate the rate constant. So remember, the rate constant can be calculated using this formula, that is fxk plus 1 minus fx star divided by fxk minus fx star. And so that's what I have done here in this particular line of code where I use rate here. And so after I do that, I print this rate. So this is the function here. Remember, if you have a list, then len gives me the length of that particular list, and I'm going from 1 here because I don't want to deal with 0, so I'm using I and I minus 1. Of course, if you like, you can use I plus 1 and I also, then you don't need that. Let us look at each of these features. So the exact solution is printed out in this form. Now remember, Python is using some complex numbers here, so it's giving me this plus 0 into j. So this is the imaginary part, which is 0, but you can see the exact values and the exact values here. So Python is very powerful. It actually has an enormous number of built-in libraries which you can use to your advantage. I also get the optimal value of the function as this number here. Let us also now just look at the convergence of the method. So again, the step size values are given here each time. The value of x as starting from 5 minus 5 and converging to the optimal. And then as these iterations go through, that's also printed out here. And each time I'm printing out the f value, so you see, since I'm starting pretty far from the optimal point, the x value is very large, but it quickly converges, and finally I get the value which is very close to the exact solution. Let's now finally print out the rate constant. So at each k or at each I am printing out the rate constant here. I is what I'm using in the code, but k is what we are using in the math. So again, you see the rate constant is somewhere near zero point 0.1, and you can clearly see that the rate constant is converging to some value here. So this is typically the case. So this also proves to me that this algorithm is essentially having linear convergence when the rate constant is around 0.1. So this is something very interesting. The steepest descent method has linear convergence. There are algorithms like conjugate gradient which have superlinear convergence. There are algorithms like the Newton method which have quadratic convergence. So when we look at those algorithms, maybe we'll check those out. So today's lecture, or rather tutorial, you learned a lot of things. You learned what is rate of convergence and rate constant. That's something very important to know. So essentially, this is not only applicable to optimization, but even if you are doing something in numerical analysis, maybe you are doing a bisection method, maybe you're doing a Newton-Raphson method, the same kind of philosophy is going to apply. At every iteration k, you will have a ek, which is given by xk minus x star, where x star is going to be the actual optimal point. It can be the optimal value, it can be the root of the function, and so on, and xk is going to be the current point. And of course, convergence means that as k tends to infinity, ek should become 0, and the rate of convergence is given by this formula here, which means that limit as k becomes infinity, norm of ek plus 1 divided by norm of ek to the power r equals c, where c is a finite value. So for optimization problems, we can track c by using the function value. So for steepest descent, of course, you have linear convergence, so it's pretty easy. But different methods, you can figure out what is the convergence rate by checking out the value of this particular estimate. So if you were to print out ek, for example, you will, after some time, some mathematical jugglery and doing some numerical analysis, you will be able to figure out what is the value of r and what is the value of c. So that's something which often plays a big role, and it is something which is important in the practical application of different methods out there. Now, one of the reasons steepest descent is rarely used in practice is because linear convergence is not something which many people want, because you are converging too slowly. So even the fact that you have superlinear convergence like in conjugate gradient methods is very attractive, and that's why those methods are intensely popular, as well as quasi-Newton methods, which we are going to discuss later in this course. So again, take a look at optimization lecture 14 for rate of convergence and lecture 13 for steepest descent method, and stay tuned to the optimization playlist because I keep releasing videos every now and then. And do subscribe to my channel if you have not already done so, and spread it among your friends and your network who may benefit from all these tutorials I keep uploading.